Hi there, welcome back. Today I want to speak with you about dependence. Now we know that dependence is an extremely important topic in risk management, notwithstanding the fact that in many models, as we have seen, we assume independence. We know that independence is a very strong and I would add dangerous assumption, and that's why we need to measure the dependence between the different quantities we might be interested in, between the PDs of two different counterparties, between, for example, the LGD and the PD, and so on. Because in real life we know that independence is not at all a plausible situation. Now, when I speak about dependence, I'm pretty sure that what comes to your mind is correlation. Now, correlation is a nice measure of dependence, but it's a very special measure of dependence. It's a measure of linear dependence. So, is not always the right measure, and I will show you in a minute what are the points of strength and the points of weakness of this measure. Because it's very important that every time we use correlation, which is probably the most used and abused measure of dependence in finance, we really need to know what we are doing. So, let's start. If we consider two random variables x and y, their correlation is defined as the ratio of the covariance between x and y over the product of the standard deviations, that is to say, sigma of x and sigma of y. Now, the range of variation of the covariance is minus infinity plus infinity. On the contrary, the range of variation of correlation is between -1 and 1. Correlation is a measure of linear dependence, which gives us two very important pieces of information. The first one is the sign of this relationship. Is it positive or negative? So a correlation moving towards 1, a positive correlation, will indicate a positive linear relationship, a negative one, a negative linear relationship. The second information is how good this linear relationship is. The higher the correlation in absolute terms, that is to say the closer to 1 or the closer to -1, the better our linear relationship describes the dependence between the two random variables x and y. In practice, a correlation of 1 means that all our observations are exactly on a straight line. Since correlation is a measure of linear dependence, if we know that the relationship between x and y is not linear, we should not use correlation. The risk is to draw the wrong conclusions about the phenomenon that we are taking into consideration. Please also notice that if x and y are uncorrelated, this just tells us that x and y are not linearly dependent, but they could be dependent in another way, in another form of dependence, quadratic, logarithmic, wherever you want. So please remember that uncorrelated random variables are not necessarily independent, while independent random variables are for sure uncorrelated. Another important aspect to underline when we deal with correlation is that correlation does not imply causation. What do I mean? If I know that x and y are correlated, I cannot say that x causes y or vice versa. And the reason is very simple. Assume that x and y depend on a common factor that we call z. Z is what generates x and y, for example. But then what do we have? If we compute the correlation between x and y because of the presence of z, we will find some relationship between the two. But x and y are not generating each other. So it's very important never to read correlation in the wrong way. If I know that x and y are correlated, I can say that they move jointly in a given way. I can give interpretations about their joint behavior, but I cannot say that one generates the other. Obviously, in the specific case in which I know that x causes y or vice versa, in that case, correlation will coincide with causation, but it's a very special case. So I repeat, I know I can be boring, but I think it's very important to underline this. If x and y are independent, then they are for sure uncorrelated. But if x and y are uncorrelated, we have no guarantee about the fact that x and y are really independent. Now, there is an important exception, and this is the exception on which we build most of the models of credit risk. So it's a little bit like cheating. And this exception is the exception of normality. If we have that x and y are jointly normally distributed, so they follow, for example, a bivariate normal, or in the case of more random variables, we consider a multivariate normal, or we can also assume different marginals, but we assume a Gaussian copula in order to model the dependence. Or even more, we relax the assumption of normality, but we restrict our attention on a slight generalization of normality, which is represented by elliptical distributions. Okay, in all this framework, the only type of dependence we are really interested in is linear dependence. When we assume normality, we are essentially assuming a linear world. In that sense, if linearity is the only form of dependence, correlation is a wonderful measure, is a measure which is completely able to capture all information about dependence. And if we are in a normal world, if we are in an elliptical world, essentially what do we have? If two random variables are uncorrelated, then they are also independent. Why? Because if we live in a world in which the only form of dependence is linear dependence, if there is no linear dependence, there is no dependence. That is to say, independence. Now, the correlation between x and y is equal to 0, that is to say, x and y are uncorrelated, when the covariance is equal to 0. And this comes from the very definition of correlation. Remember that the numerator is the covariance. Now, in the case in which x and y are independent, we know that the covariance is actually 0, because the expectation of the product is the product of the expectations because of independence. In this situation, covariance is equal to 0 and correlation is equal to 0 as well. Now consider these two cases. In the first one, we first define a random variable u, which is uniformly distributed on the interval -1, 1. And using u, we construct x and y, as you see on your screen. Now, in the second case, we take x to be a standard normally distributed random variable, and y is constructed as x squared. Now, it's not difficult to show that these random variables, these couples of random variables, are uncorrelated. Why? Because their covariance is 0. The covariance between x and y in both cases is 0. But it's not difficult to see that they are not independent. If I know that y is equal to x squared, how can I say that y is independent from x? Now, I want to share with you some hints about the graphical interpretation of correlation because it may seem simple, it may seem obvious, but actually it is not. And you will see in a minute. First of all, notice that correlation tells us how good the linear relationship between x and y is, but it is not a measure of the slope of the linear line that we can use to represent this relationship. Just consider the three pictures in front of you. In the three pictures, the slope of the red line is always the same. But while in the picture on your left, the correlation is equal to 1 because we have perfect positive linear dependence and all the observations are exactly on the line. In the last one on the right, correlation is equal to 0.4. We can still see a positive inclination of the observations. We can still see a positive linear relationship, but it is less precise. The observations are more scattered around the red line. The red line will represent the major axis of the ellipsoid containing the observations. And this should also make you understand why, under normality, correlation is the perfect measure of dependence. The trick is exactly in the ellipsoid. The fact that correlation is not a measure of the slope is even more evident in the three plots you see on your screen. In all the three situations, we have a correlation of -1, that is to say, perfect negative linear dependence. All the observations are always on the straight line, but it's clear that the slope is not the same. Now consider these four plots. In every single plot, correlation is equal to 0, so x and y are uncorrelated. But could you really say that they are independent? And what about this plot? Are x and y uncorrelated? Yes, they are. You can also read 0, so it's easy to say that they are uncorrelated. And are they independent? Yes, in this situation they are independent. When you have a circle of this type, so when your cloud of points tends to fill a circle, then it's a good signal of independence. Why? Because think of the ellipsoid. The ellipsoid is becoming a circle, and for a bivariate normal, this happens exactly when the two marginals are independent. Otherwise, you will always have an elliptic behavior. In reality, it is quite difficult to obtain a correlation which is exactly equal to 0 unless you create fictitious data as the ones we have just seen. So when you compute correlation with your computer, with R, MATLAB, Excel, whatever you want, you will always find a correlation which is small, maybe very close to 0, positive, negative. So one could be inclined to believe that, okay, maybe there is no such a strong linear dependence, but we can see something. No, in the cases I have just showed you, it's wrong to use correlation. So please just plot the data and then you decide if correlation can be the right measure for you or not. Now consider this last plot. We have 4 different subplots. What do you think is the plot with the highest correlation? And what is the plot with the lowest correlation? Actually, correlation in these plots is always the same. It's 0.816. These 4 plots are known as the Escombe quartet, and they have been created by Escombe, a statistician, to show the weaknesses of correlation. Actually here, if you compute the mean and the standard deviation of x and the mean and the standard deviation of y, they are always the same. So be careful when you deal with correlation. Linearity, especially when it's not the good model, can be a rather tricky object. So what are the alternatives that we can use instead of correlation? Actually, there are many possibilities. We will just consider some of them in the next class. So for the moment, I thank you for the attention and goodbye.